So we'll start with 12.1. Now this concept is going to seem very different than everything we've been doing up to this point. Chapter 12 is called Systems of Equations. Do they say linear? No. Equations and inequalities. So I'll start with an example here. Can somebody tell me a solution to that equation? In other words, give me an x and give me a y that make that true. Give me an x and a y that make it true.
X equals 4.
X is 1. Y is 1. Everyone agree that that would work?
Or even x is 0 and y is 4.
You could do x is 0, y is 4. Would that work? Yes or no? Yes? Both of those would work? Are there any more? How about x is 4?
And y is negative, what, 8?
Y is negative 8 would work? And we could actually spend the rest of our lives finding pairs that would work. All right? And if I were to sit there and look at those as ordered pairs, like 1, 1, the next one 0, 4, and the next one 4, negative 8, if I were to graph those on an xy coordinate plane like this, guess what it would draw? Yep. Go with your instinct. A line. Why?
Because it's linear.
That's a linear equation, right? If I solved that for y, wouldn't it be a line? Y equals mx plus b. So all of the solution sets together would actually graph that line. Yes? Okay. That's not what this is about. But it's connected to this, all right?
Well, shit.
Okay. Okay. So but we have to understand this first. So we have in this chapter equations. Here's an example of an equation, yes? But instead of just one equation, we have what we call a system of equations. That means you have more than one equation together. So now what I'm going to do is I'm going to erase this, and I'm going to put 2x plus 3y equals 12. Now I have both equations together, right? If you were to ignore this top equation, right? If you were to ignore this top one, we could sit here and do the same thing and come up with a bunch of answers, couldn't we? Yeah. And if we plotted them all, it would be a line. What we're interested in, though, is looking at these together as a system. So we put a brace in front of it to let you know that we want to look at these two equations at the same time. And now what we want is we want to try and find an x and a y that work in both equations simultaneously. So an x and a y that makes this true at the same time that it makes this true. Can anyone see what it is?
I feel like it's a 4. 3 for some reason.
It's not that easy, is it?
No.
Just to look at it and see it? Does 0, 4 work?
Yeah.
Yes.
Dang.
All right, 0, 4 works. Now, geometrically, what do you think this 0, 4 is if you were to graph it? Like if you were to come over here, 0, 4 would be a point right here, right?
Vertical axis.
No, think about it. Hold on. What is this right here if we graphed it? What is this one? A line. What is this one? What do you think this point is where they hit each other? All right, that's what it is. It's a point that exists on both lines at the same time. So if we were to graph this one, I'm not saying this is the correct graph. I'm just going to say that's maybe that line. And then this line could be doing something completely different. And that point where they hit each other is the point of intersection. That's geometrically what we're doing when we solve a system of equations like this. So we're trying to find a point of intersection of two lines. Understand?
Yes.
Okay. So this right here is an example of what we call a system of two linear equations in x and y. So let's go through and read through that and see if we understand what all the words in that mean. System, meaning more than one, of two, not three, not five, system of two, linear equations, because each equation is linear. How can we tell it's linear? Each of these variables are to the first power. That's how we can tell an equation is linear, if your variables are to the first power. And then in x and y just tells you the two variables within the problem. All right? So if I were to give you a different problem like this, 3s minus 4t equals 5, and s plus t equals 10, we would say that this is a what? System of two linear equations in s and t. All right? So now let's talk about what type of solutions we should get when we're dealing with something like this. Given two linear equations in two variables. So this could be like x and y. Could be r and s, could be s and t, could be v and w, doesn't matter. But if we're given two linear equations in two variables, one of the following is true. One. So think about it. Geometrically, the solution to this system of equations is the intersection of the two lines, right? How can that happen? I mean, how many answers could you possibly get? If I have two lines, right, sitting out there, they could intersect each other in one point, right? So you could have one solution. And geometrically, that would be this scenario right here. A line, another line, their intersection point, right? That's what one solution would mean. But there are two other possibilities of what could happen. What are they? What if they're parallel, right? What if the two lines are parallel? No solution, which would look like this. You have two lines that are running parallel to each other like that. And what would be the third solution? Or the third type of answer? What if they're the same line? Then they hit each other where? Everywhere, which means you have infinite number of solutions. Infinite, not, okay, we have to be careful. Infinite solutions. It's not all real numbers, but there are an infinite number of points where they hit each other. So this is kind of hard to draw, but it's a line, and then the other line is the same line on top of it. So they hit each other at an infinite number of points. Okay? So what we need to do now that hopefully you have some understanding as to what a system of linear equations in two variables actually represents geometrically and the types of answers we can get, we need a systematic approach as to how we are going to get the answer or figure out which of these it is, right? Some systematic way. So there are two commonly accepted methods for solving a system of linear equations in two variables. So there are two methods for solving a system of two linear equations in two variables. Now that gets kind of to be a pain in the butt to write over and over again, right? System of two linear equations in two variables, right? Would you agree? So we're going to start using shorthand notation, and this is going to come up in the next section, which we'll do next week, which has to do with what are called matrices. All right, the number of equations you have, you write down 2. And the number of variables that you have here is 2, right? So we could call this system a 2 by 2 system. It's 2 equations, 2 variables, right? A 2 by 2 system. A 3 by 2 system would be 3 equations and 2 variables, right? What would happen in that case? What if you had 3 equations and 2 variables? What would your answers look like? Think about it geometrically. What does 3 equations mean? 3 lines, right? What would the solution to this system of 3 equations and 2 variables be?
That one, you have 3 answers.
Would you have 3 answers? What does this point? This point makes just those 2 true, right? But not that one? This one makes just those 2 true, not this one. This makes these 2 true, but not that one. So for this particular situation, you would have what?
No solution.
You would have no solution. There's no point that all 3 lines hit at the same time. You would have to have something like this in order to get that to happen. That would give you a solution, right? That's too complicated. I'm just getting you to try and think about how changing that to a 3 changes what you're looking at, right? Okay, so there are 2 methods for solving these. The 2 methods are called, anybody know what one of the methods are called? Elimination. I'm going to actually write it. I'll do substitution first. Substitution. Substitution. There we go. And then the second one is called elimination. Now, we are under time constraints here because we're at the end of the semester. We only meet 2 more times, right, after today? That's it. Next week, that's it. We're done. Substitution is usually the easiest, and it's usually the fastest. Usually, not always, all right? Little asterisk there. It's not always the easiest and fastest, but in general it is. The weakness, though, is that this is only good for, only useful for 2 equations, 2 variables. If you go past 2 equations, 2 variables, substitution becomes very tedious and difficult. All right? So if I give you 3 equations with 3 variables, then substitution is not something you want to do. Elimination now, the other method, is slow and methodical, but always works, or works for I put n by n. What do I mean? Any number of equations and any number of variables. 5 by 5. You could have 5 equations and 5 unknowns, and elimination would work for that. In fact, on a computer, there are algorithms built into the computer that will do a solution to a system of 5 equations and 5 unknowns. And the algorithm written by the computer scientist people who write the code for the computer use elimination to get to the answer. That's what they do. So because of this, I am going to show you elimination. That's what I'm going to show you. Because it's more powerful. And it can be extended to 3 by 3, which is also what we plan on doing in here. All right, so you ready to see it? Good. Thank you, Lily. So let's go to that example that I had on the board just a little while ago. See if I can remember it. Was it,
3x plus 1 equals 4, and 2x plus 3 equals 12.
it was plus between the, on the second one? Okay. So we already know what the answer, it was plus, up, oh, on top, plus here? Okay. So we already know what the answer is to this, right? I told you what it was, but we said it would be hard to just like look at it and be like, oh, sure, 0, 4, right? So let's now use this method called elimination. And I'm going to start doing it, and I'm going to ask you whether or not you agree with what I'm doing. Like, can I do it or not? All right. So first thing I'm going to do, I'm going to look, make sure this is in proper order. So I'm going to have like my x's are lined up, my y's are lined up, I have an equal sign, I've got a number. Right? Once they're all lined up, I'm going to look at my x variables and my y variables separately. Look at the x's. If you were to put these two together, when I say that I mean add them, what would you get? 5x, right? What you're looking for is to add them together and get 0. So if I add these together, I don't get 0, right? If I add these together, I get 4y. I still don't get 0, right? So I need to somehow come in here and tweak it to make it add to be 0. So what I'm going to do, go ahead, Lily. What do you want to do?
Multiply the top by -2 and the bottom by,
You could do that. Hold on. I'm going to do the y's instead. Watch. Look at this y and 3y. If I take this top equation, I'm putting -3 out there, and what that -3 means is I'm going to multiply everything by -3. Am I allowed to do that with an equation? If I have an equation sitting here, 3x plus y equals 4, can I multiply everything by 3 and it still be the same equation? Yes, because that's the same as multiplying both sides by 3, right? Or sorry, -3 is what I should have said. But what effect does that have? Think about what would happen if I put a -3 through. What would it do to that y? Turn it into a -3y? And then when I put those together, what would I get? A 0. So what I'm trying to do is tweak this top equation so that when I add the two equations together, at least one of the variables goes away. Right? And then we'll go from there. Now, what Lily was saying, and this is correct also, that's not the only approach that you could have taken. You could have also tried to get the x's to cancel. But the x's are a little harder because one of them is 3x, the other one is 2x, right? So watch what we could do. I can multiply the top by 2, right, through everything. That would give me a 6x. And then the bottom by what? -3. And then when I multiply that through, I would get -6x, wouldn't I? I'd do them both at the same time. And that would make the x's cancel. This way is a little bit harder, I think, than this way. But we have to know how to do this also, because I'm going to give you an example where you have to do this. All right, there's no options. All right, so the way we write this now, the proper way to do this is to draw an arrow, rewrite the brace, okay? Multiply the -3 through the parentheses, or through the top equation. You get -9x, you get -3y, you get what? -12. And then the bottom equation we didn't touch, right? We didn't touch that equation? Any questions? Rewriting the entire system of equations is something that I want to see because, again, we're going to go to a 3 by 3, and it's going to be hard to keep track of things. You just don't want this to be scratch, just chicken scratch work on the side. You want it to be very systematic. All right, so the next thing that we do is we add the two rows together. All right, we add the two rows together. So I'm going to just add straight down. And this is where my brace will go away. All right, so -9x, add it to 2x, what do I get? -7x. I add the y's down, I get +0. And then I add these, and what do I get? 0. Now this is an equation, isn't it? Now it's an equation with one variable. I have eliminated, right? I have eliminated the y. That's why they call it elimination. We have gone from a system of two equations and two variables. I've eliminated the y variable by doing this nice little multiplication. And now I have a nice equation I can solve. Negative 7x equals 0. And to solve that for x, you do what? Divide by negative 7 on both sides. And of course, that just gives you x is 0, right? Yes?
And then you plug it into one of the two equations. And
Which one?
from the first set.
Okay, so now what we do is we do what is referred to as the back substitution step. We know what x is, right? All we need to figure out now is y. But every single one of these equations sitting in front of us has a relationship between x and y, right? So I go and I need to grab one of them and use one of them. And the one that you use can be any of them, all right? I could use this one right here. I could use that one right there. I could use this. It does not matter which equation I grab now. But the common rule of thumb is to go back to the original system because you know there are no mistakes in the original system because that's the way it was given to you, right? So my back substitution now, back substitute. I'm going to pick the first equation up there, 3x plus y equals 4. And then what was x? 0, so 3 times 0 plus y equals 4. And of course, 3 times 0 is 0, so y is 4. And so what we do is we like to write our answer as an ordered pair. We like to write it as a point, almost like a point, like an x-coordinate and a y-coordinate. So 0, 4. That would be my answer. You don't have to write the x and y. I'm just telling you that's what. You don't want to write it the y then the x. What do y'all think? Pretty straightforward? All right, let's try one that's a little more challenging. Yep, I'm not going to do substitution. All right, so how about negative 5x plus 3y equals 4, and 7x minus 2y equals negative 3. Nobody in here is going to just look at that and tell me what the solution is. It's not going to happen. If you can, you probably don't belong in here. Oh my God, no, just kidding. I don't even know what it is. I mean, I wouldn't even try. It's not worth it.
If it's 3 and 7, I get an A.
You're gone. You're out of here. You get an A. I'll get you the degree without doing anything else. No. So system of equations, right? 2 linear equations and 2 variables. I'm going to use elimination. So I need to try and eliminate one of the variables. Which one would you like to eliminate?
Why?
Why?
Because it's small and the smaller values.
Okay, so you're just going to go with the y's because you want to? I agree. I mean, either way, you're going to have to do some work, right?
Common, or not common denominator, but an easier common factor.
Yeah, I mean, there's a number. You see, you're going to have to turn these both into the same number, right? Just opposite in signs. So the common multiple of these two is 6. Where over here, the common multiple is 35. But, yes? Oh, are you going to tell me what to use?
Yes.
All right, what do you want to use?
2 on the top and then 3 on the bottom.
Why not negative 3, Lily?
Because if you do negative 3 on the bottom, it's going to turn into a positive 6, and when you add them up, it'll be 12.
That's right. So you have to pay attention to the signs here. In the last problem, one of them was negative, wasn't it? Because we needed, when we multiplied through, for these two to be off by a sign. Here we don't need that because they're already off by a sign. So I rewrite the system because I'm not lazy. Is that right? What? This is incorrect, right? That's one of the mistakes I see a lot, right? Where it's like you're multiplying through and you forget just one multiplication. What do you think happens if you just forget that one thing? It's everything's gone. It's all over. Game over at that point. Now what? Add them down, right? Add these down. And when you add them down, you get 11x plus 0 equals negative 1. X is negative 1 over 11. And that's it. We're not going to go get our calculator out and get a decimal or anything like that. We're just going to leave it as negative 1 over 11. What do I do with that?
Take that and bracket first.
Go back to any equation we want. So back substitute, I just call it the BS step because I like to just say BS. We're going to back substitute into any equation. You wanted me to pick the first one?
Yeah.
Yes? What was it? What do we multiply by? Negative 5x plus 3y equals 4. Is that it? All right. And I'm going to replace in that equation the x with negative 1 over 11. Negative 5 times negative 1 over 11 plus 3y equals 4. And yes, you have to work with fractions, all right? What is negative 5 times negative 1 over 11? Positive 5 over 11. So this is 5 over 11 plus 3y equals 4. And if I'm going to solve for y there, shouldn't I isolate the 3y term? So that means I should subtract that on both sides? So I'm going to take 4, and I'm going to take away 5 11ths. How am I going to take 5 11ths away from 4? What's the proper way to do it?
2.2.
Oh, no decimal. How do you subtract 5 over 11 from 4? You have to get a common denominator. So 44 over 11 minus 5 over 11. How many of you are planning at some point to take calculus? Okay, you've got to get comfortable with fractions. It's just, you just have to. You have no choice. You either do it now or you suffer later for it. 3y equals what now? 39 over 11. And then divide both sides by 3. So if I divide by 3, what's going to happen? Multiply by the reciprocal. So I could just say this instead. Multiply both sides by 1/3 is the same as dividing by 3. And this will give me a y over here. And then multiplying straight across, 39, 33. Oh yeah, you can reduce that. 3 goes 12 11ths. Of course that's the answer. Negative 1 11ths, 12 11ths. You were off just a little bit, Nathan.
What did I say?
Like, I don't know, 7 and 3 or something like
That's
that.
close. That's close.
Pretty close.
Like the 1 plus the 2 is a 3.
All right.
You're wrong, sir.
Okay.
It's 13 11ths.
What did I? Oh, yeah. I didn't. I was just listening to what it was supposed to be. Yes, that is 13 11ths. Right? 3 goes into 39 13 times. 3 goes into 33 11 times. Thank you. We good? Yes? All right. So what if you have a system like this then? 1/3 x minus 4/5 y equals 3, and 2x minus 7/3 y equals negative 2. It's the same story, right? I mean, we're trying to eliminate one of the variables. It's not so obvious, though, right? I mean,
Get rid of the x's first.
you want to try and get rid of these x's?
Yes. 10 to the top by -6. I mean, yeah, -6.
So if I do the top by -6, what am I going to get?
You're going to get -2.
-2, and that would cancel there, wouldn't it? Yes? Now, I think that that works here, and if you see it, you see it, but I'm going to do just more of a systematic approach, okay? Y'all don't like fractions? And I do, but that's okay. I'm going to clear the fractions. So look at this whole equation right here, and tell me what a common denominator would be for the whole thing, 15. So let's just multiply that whole thing by 15. What's a common denominator here?
6.
These are all over 1, right?
Then 30.
So just a 3. Let's multiply this by 3. What effect should this have if I do this?
You get all whole numbers.
We're going to get all nice whole numbers, right? And at least we'll be able to work with that a little easier. So multiply 15 through the top one, and what would you get?
You get 5x
5x.
minus 3. Well,
So I'm multiplying 15 times 4/5, right? So 5 goes into 5 once, into 15 3 times. 3 times 4 is 12. You should get 12y. And then the other side? 45. Yeah, you could have also just said it's 60 over 5, right? Here, what would I get on this one? 6x minus 21 over 3, so 7y equals negative 6. And now that hopefully is a little bit easier to deal with.
So change x's.
You want to clear the x's? Now, Lily, if you were to have done what you were suggesting, I think you would clear the x's pretty nice. I think the rest of it would be kind of ugly just with fractions, right? Because you don't clear any of the fractions. Here might be a little bit easier to work with. Let's just keep working this, all right? Clear the x's. What are you going to do to clear the x's? Top by 6 or negative 6. You could have used negative 6. This one by negative 5. So does everyone see you could have done negative 6 here and positive 5 here? Or positive 6 and negative 5? I rewrite the whole system again. Distributing 6 through. 30x minus, starting to get big numbers, right? 72y equals, what is it, 270? 270. And then the bottom one, negative 30x and 35y equals 30. Now they're off. These are perfect, right? 30 and negative 30, sorry, 30x and negative 30x. So when I add down now, I'm going to get 0 right here. And then how many y's?
Negative 37.
Negative 37 y's. I agree. And then equals what? 300. And divide both sides by negative 37. Ugh. Yeah, I'm going to leave it just like that. And remember, that is the same as negative 300 over positive 37, and that's the same as negative 300 over 37, right? With negatives on fractions, the negative can be on the bottom or on the top or out front. They're all equivalent. Right, so now I have the pleasure of taking that number and going back to any equation I want and plugging that in for y. Which equation would you like to go back to?
2x1.
You want to plug it into the one that has fractions in it?
Only one fraction. Well, it only has one fraction.
It does, but it's the y that has the fraction, doesn't it?
Yeah.
It doesn't matter where you go with it. It really doesn't.
It's tough to get a common denominator.
You're still going to need you're still going to need to work with fractions. So which one do you want?
Let's do that one. The 2x.
Okay, so it was the back substitute step. It was 2x
Minus 7/3 y
minus 7/3 y
equals -2.
negative 2. And I'm replacing y with negative 300 over 37. So 2x equals 2x minus 7/3 times negative 300 over 37 equals negative 2. Ugh.
Calculator. Well, for,
I like that 3 and 300 are going to reduce, aren't they? Look, like this 3 goes into 300 100 times, doesn't it? And when I take this number and multiply times this and then subtract it, won't it be the same as adding? Right? So double negative, right? So isn't this going to turn into 2x plus, let's see, 100 times 7, so 700 over 37 equals negative 2. Going to move the 700 over 37 to the other side. I already have a negative 2 there. I'm subtracting 700 over 37. So how did you do that? You calculator? You get a common denominator here though, right? That's a negative 2 over 1. Multiply 37 top and bottom. So you have 2x equals, what is negative 2 times 37? Negative 74. So negative 74 over 37 minus 700 over 37, which is negative 774 over 37. We're almost there. Finally, divide both sides by 2 or multiply both sides by 1/2, however you want to do it. I like the multiplying by 1/2. And you could multiply 2 and 37 here, or because that's an even number, doesn't 2 go into that? Doesn't 2 go into 774? What is it? 387? 387? That's about as ugly as they'll get, okay, when it comes to me asking you to solve a system of 2 equations and 2 unknowns. This is where I give you fractions and your answers are nasty fractions. I expect you to work it out as fractions, though. I don't want to see decimals. I want you to show me that you're ready for pre-cal, that you're not afraid of a fraction still. All right. Now, nobody questioned me when I started doing this. Everyone was pretty much on board when I did the problem and I said, okay, take your equation, you can multiply a number out here, right? Like 2. Everyone agreed, I mean, that doesn't change it, right? But no one questioned me when I said when you add the 2 down, that it's still going to maintain everything. Like nothing's going to get screwed up, right? You just trust that that would work?
yes.
Okay. And it does. But the person who came up with that method that showed that it was okay to do that was a mathematician, last name is Gauss. I believe that's the way you spell it. And the method that we're actually doing, or starting to get close to, is called Gaussian elimination. But we don't usually tell students it's called Gaussian elimination, we just call it elimination. Right? But it is because of a method developed by Gauss. So I want to tell you all a little story. Since it's Thanksgiving's close, it's around the corner. I'm going to tell you a little story about Gauss. I don't think I've told you this story yet. Yeah, it's story time. Okay, look. So Gauss was a brilliant, brilliant, brilliant mathematician. All right? He, if you go and look up Gauss, if you Google Gauss, you'll see all sorts of things he did. But here's the story. His dad was an accountant, and he used to sit on his dad's lap while his dad would do the accounting. And this was back in like the 1800s. And so everything was done by hand. So his dad would have all these numbers in this column. He'd be adding them up. And Gauss, so the story goes, could add these numbers up in his head before his dad could do it by hand. And this is when he was like very young, like 4 years old, something like that. And then the most famous story, and whether or not this is true or not is debated, but it's a great story, is that when he was in first grade, the teacher went into the class and said, class, this is first grade, all right? Class, what is 1 plus 2 plus 3 plus 4? And the little first graders sat there and broke out their phones. No, wait, no, they didn't have phones. They broke out their, nope, they didn't have calculators. So what did they do? The little first graders said what? They sat there for a second and then they said what? What did they say?
12.
Okay, right? 10, yes? So the teacher says, all right, good, very good, class. What I'd like for you to do now is I'd like for you to add up the first 100 numbers. Get to work. Okay, and so it was one of these days where the teacher didn't really want to deal with the students. So just give them some busy work, you know, and the teacher went and sat down. And within a few minutes, Gauss took his little slate, because they used to write on little like chalkboard slates in class. And so he took his little slate and he turned it over and he crossed his arms and he sat there quietly. Because back then they also had discipline and, you know, lots of things like that. So he just sat there quietly, very obedient. Teacher kind of looked up at him, went over to Gauss, turned his slate over, and this is what Gauss had written down. Don't call bullshit yet, okay? N times n plus 1 over 2. So the teacher being, you know, a teacher, and I think back then even elementary math teachers would have known that this formula exists. This is a well-known formula for the sum of the first n numbers, right? So the teacher recognized the formula. He knew that this formula worked. In fact, I'll show it to you real quick. If you want to add up the first 4 numbers, then we will call the last number right here, we'll call that n, okay? If you take n and plug it into that formula, what would you get? So 4 times 4 plus 1 divided by 2 is 4 times 5 over 2, which is 10, isn't it? 20 over 2 is 10. So it works for 4, but guess what? It works for 5 and 6 and 7 and any number, okay? That formula works. So the formula, like I said, was well known already in mathematics. So the teacher got all pissed off and was like, you know, who showed you that? And Gauss trying to explain to him, like, nobody showed me this. Like, and the teacher got very, very upset, you know, Gauss is lying to him. So Gauss went on to explain how it is he got the formula. And I'm going to show you the explanation. And I know some of you will follow this. I think most of you will follow this. Okay, so Gauss said, here's how I did it. He said, I'm trying to find the sum of the first 100 numbers, right? So let's just call that, I'm going to call it x. I don't know if he called it x. I don't know what he called it. 1 plus 2 plus 3, all the way out to 100, right? So the last number out here is 100. What's the number right before it? 99. What's the number right before that? 98. And before that, you know, there's a bunch of stuff. Now, we know with addition, and only with addition, that the order in which you add things doesn't matter, right? 1 plus 2 is the same as 2 plus 1. So Gauss said, well, I may as well have written x this way, backwards. And I would do the same thing, wouldn't I? I mean, I should get the same answer. What's the last number going to be? 1. The one before that? 2. The one before that? And then a bunch of stuff, right? And then Gauss noticed that if you take this, like 2 rows of things, and you add straight down, this plus this, so this side of the equation, if we add these 2 together, what do you get? Twice as much as what you want, right? Twice 2 of the sums you're looking for. Twice as much as what I want should be this added to this. But look, What's 1 plus 100? Okay. What's 2 plus 99? 101. What's 3 plus 98? 101 again, right? What's 4 plus 97? 101 again. In fact, they're all 101s, right? Even down here. 101. The one right before it, 101. The one before that, 101, right? They're all the same. How many 101s would you have? Think through it. Don't just spit an answer out. How many would you have? Well, you have one of them here, right? Then 2, then 3, then 4, then 5. You will have 100 101s, won't you? So twice 2x, I'll put it up here. 2x should be equal to 100 101s. 100 times 101, right? That's the same as adding 101 100 times. Multiplying is repeated addition. So that's what that means. And then divide both sides by 2, and you get x. So if I divide both sides by 2, I get what that sum would be, right? Now, I lied to you a little bit here, because this is not exactly the way Gauss explained it. Gauss was smarter than that. He didn't stop at 100. Okay? He stopped at n. So when he's explaining it, he said, you want me to add up the first n numbers. There they are. What's the number right in front of n? Well, it's 1 less than n, right? So why don't I call it n minus 1? What's the number right in front of n minus 1? It's that one minus 1 again, right? So isn't that n minus 2? Yes? Yeah. Then if I rearrange it and write it backwards, this one will be an n. The next one will be n minus 1. The next one will be n minus 2. All the way down, the last number will be what?
N minus 100?
No, no.
1 minus
1. The one before that? 2. The one before that? 3. All right? Do y'all see that? I know some of you do. If you're lost, it's okay. You're not going to be tested on this. All right? So then he said again, I'm going to add straight down, and he noticed a pattern. N plus 1 would be the first thing he gets, right? N plus 1. But what would the next one be? Yeah, what's n minus 1, but then plus 2? That's n plus 1 again. So he's going to say n plus 1. I'm going to have another n plus 1. Then when I do this one, I'm going to get n minus 2, but then plus 3. Or no, sorry. N, yes, so n minus 2 plus 3 is n plus 1 again. And I do that all the way to the end. And my very last one is also n plus 1. Now, very careful. How many would he have? 1, 2, 3, 4. He would have n of them, wouldn't he? So 2x is n plus 1s. And divide both sides by 2. And you get the formula that he
did this in
first grade. That's exactly what I was saying. So how many of you felt like you kind of followed what I did there? Yeah? Yes? Okay. So it's not that like crazy as far as like the idea now that you've seen it, right? But this is what separates geniuses from us. And I'm not trying to say we're not geniuses. Maybe you're an artistic genius, but nobody in here is a mathematical genius like this, or else you wouldn't be in here. I'm not a mathematical genius like this. This is a first grader that understands how to attack something like this. It's very simple, but to understand that at such a young age, these types of people don't come along very often. So, it's quite beautiful, isn't it? That a little first grader could come up with that. Now, also keep in mind that first grader back in 1800s is probably like 8th grader nowadays. Most likely. I shouldn't say I don't know for sure, but this, Google this. They pulled a, you know how high schools will do like time capsules and stuff like that? They pulled it like a test from a high school, like a senior like final exam. They used to have like almost like final exams and stuff. They had like a final exam for seniors for this high school somewhere in the United States 100 years ago. They pulled up that time capsule. Go Google that. Go take a look at that test.
Was it hard?
Yes. Yes. So everything, all the standards, all the things have come down. You know, all of our, and that's why we have trouble competing in this world. That's why we're behind everyone in mathematics and science. And that's why there's such a push for STEM to try and get people, you know, to invest in it, to try and get us back up to where we used to be. Because in the 50s, in the 60s, I mean, we were the leader, right? We were the leading country. So we're trying to get back to that, but the problem is that it starts young. You have to teach kids at a young age that mathematics is something to be appreciated and to be enjoyed. And the problem, I believe, is that students at very young ages are being taught by people who hate math. A lot of elementary school teachers hate math, but they're teaching it. So if you don't have a passion or a love for something, how are you supposed to like help someone else find that passion and love for it? It's not really a head scratcher. It's pretty simple, the problem. We just need people who like math, teaching math, and at a very young age, because kids can soak it up. I mean, how many of you grew up, you know, through middle school or grade school, middle school, high school, and felt like every step along the way, your math experiences were always very positive things? Yes? Okay. I mean, that's rare. That's a rare thing. You're lucky if you saw that. So, all right, I'm getting too political here. All right, so we've got some time still. So what happens if we get something like this? Yeah. Sorry for going off on that tangent there. 2x plus y equals 5. 4x plus 2y equals 8. I want us to solve this. So what do you want to do?
Times the top by what, negative? Not negative.
What variable are you trying to clear?
Y.
You want to clear the y's?
Times it by 2.
That okay with everyone? Clear the y's out? You could do the x's also. It doesn't matter. But you said y, so I'll go with what you said. Negative 2 on top?
Yeah.
Well, it would cancel everything out.
Okay, hold on then. Let's see what happens.
So 0, 0.
So negative 4x, right? Minus 2y equals what?
Negative 10.
Negative 10. And then on the bottom we have negative 4x, positive 4x plus 2y equals 8. And then you're supposed to add down, right?
Negative 2.
And you get 0 equals negative 2.
They don't know.
And those are not equal, right? 0 is not negative 2? So if 0 is not negative 2, then this system doesn't have an answer, which means that these two lines don't intersect, right? Which means these two lines are parallel. That's when you know that you're dealing with that situation. So remember, we said there were 3 possible things that could happen. You could get one answer, no answer, or infinite number of answers. This is when you have no answer. When you get something that makes no sense. So we say here, no solution. And you don't say, you know how we've said in the past, like no real solution? We're not even saying that. We're saying just no solution. All right. I'm going to do another problem. I'm going to just take this. I'm just going to tweak it just a little bit. I want you to change that 8 to a 10. Change that 8 right there to a 10. And then let's see what happens. So all I changed is this to a 10. So you're going to get, when you do your 2 through the top, negative 2 through the top, your new system will be negative 4x minus 2y equals negative 10. Your bottom equation is 4x plus 2y equals positive 10. And when you add straight down this time, you get 0 equals 0. But that is true. When is it true? This is true always, right? 0 is always equal to 0? That's always true which means that these lines are the same line on top of each other. In fact, look at it. If I take this line right here and double it, I get that, right? Just 2 times each of those, and I get that. So this is the same line, so I have an infinite number of solutions, right? Infinite solutions. Now, there is a proper technical way to write down what the answers are. If these are the same lines, see if you can follow this. This always gives people trouble. If these are the same lines, then that red is representative of all the answers, right? It's the same line. So every point that lives on this line is an answer to this system. So how could I represent a point on this line? Well, I know that this value I could call x, couldn't I? And then what about the y value? How high up is it? Well, if these are both the same line, then can't I just solve that for y?
Yes.
Okay, solve this equation for y, and what do you get? Y is negative 2x plus 5. You could also say 5 minus 2x, right? That is what the y-coordinate is. So we have infinite solutions, but not just any numbers we pick. They all have to look like this. So watch. Someone give me an x, a nice x. 7. Okay, what's the y value? Negative 2 times 7. Negative 14 plus negative 9. Negative 9. That point lives on that line. It should. Let's see. Plug 7 in here. 14, right? Plus negative 9 is 5. Yes? So that lives on that. And so you can just start picking any values of x. Do you see how this represents an infinite number of answers? You give me x's, I can spit y's out all day long. But that doesn't mean, what I want you to see is that doesn't mean I can pick any freaking values I want and it work. Like 0, 0 does not work, right? Understand the difference between saying there's an infinite number of solutions and it's everything? This is not everything, right? It's just these points, which look like that. So this is what we would be looking for as a solution to this equation, system of equations. That right there.
So when we got 0 equals 0, that's not an actual whole. That just tells us that it's infinite.
That tells us we have the same line and we have infinite solutions. So there's the 3 possibilities. If you work through this and you get x equals 2, then you have to go back, substitute, and get y. Then there's only one answer. If you get something like 7 equals 4, no solution. They don't hit each other. If you get 7 equals 7, infinite number of answers, write x, and then go take any equation and solve it for y and stick it right there. Okay? All right. I'm going to cut class here in just a minute, all right? But I want to just get you introduced to the next topic. We really won't have time to get into it, so we'll do it next week. But what if we have something like this? Well, let me do this instead. 2x plus 3y plus z equals 10. Well, right now you have one equation, right? And you have how many variables? 3. This would be a single equation, right? It's a linear equation because each variable is raised to the first power, right? It's a linear equation in 3 variables. Before I get to where we're headed, which is 3 equations with 3 variables, what does that look like? I mean, you told me just a second ago what 3x plus 2y equals 5 look like. Nathan, you said that's a line, right? And we all agreed that that's a line? What's that? Is it a line? Have we ever dealt with z before? Have we ever dealt with z? No. So